Let's consider a binary classification example. Binary classification, again, means there are two classes. From the perspective of computing entropy for a random variable, imagine a case where the random variable only has two possible values. And P is the number of examples from class 1. For example, head in the coin example. And N is the number of examples from class 2. For example, tail. And let's say this is the first value our random variable can take on, and this is the second value our random variable can take on. Then P over P plus N is just the probability of V1. And N over P plus N is the probability of V2. So then the whole thing is the same as the entropy equation you saw before. The probability of Vk log of probability of Vk. And we don't need the summation sign because since we only have two classes, we can afford to write everything out. Given this, which of the following has the smallest entropy and what is the entropy? Even before we do any calculation, we know that the case 1 would have the smallest entropy because every example is from the same class. So imagine picking a random one out of these 6 examples. How certain are you of the class of the example? Well, in this case, I'm 100% certain that the example will be from the second class. In fact, there's no uncertainty, so we know that the entropy would be 0. So even before we do any calculation, we know that out of the 3 cases, case 1 will have the smallest entropy, and that the entropy is 0. So A is the answer. And we would expect that the second case will have a higher entropy. So you think it's probably from the second class. So a 5 out of 6 chance, but you're not fully certain. And then the entropy would be even bigger for case 3. And we can actually do the computation, which will just verify our intuition. So in the first case, you have 0 chance of getting the first value, which is head. And you have 100% chance of getting the second value, which is tail. And it's just 0 minus 0, so it's 0. And then as you can see that the entropy for the second case is bigger, and then even bigger for the third case, as we expected. And information gain is the expected reduction in entropy from using an attribute to split the examples. Again, the equation may look a bit daunting, but the intuition is pretty simple. So this is just the entropy before the split. And this is the weighted entropies after the split. So basically, information gain captures how does entropy change after you split the group of examples using some attribute A. If the information gain is positive, that means splitting by the given attribute reduces entropy overall. So let's revisit these examples. In both of these cases, the entropy used to be B of 6 over 12. So we have 6 yeses and 6 no's. And same thing here. One half. Now, when it comes to using the attribute type as a decision point, we end up with 4 different groups, each with entropy of B of 1/2. So we have the same number of P's and N's in each of these. And to compute the information gain of using the attribute type, we would get b of 1/2 from here minus the weighted sum of these. And you weight them by the percentage of examples that are in the given group. So 2 out of 12 went to the first group. And 2 out of 12 went to the second group. And 4 out of 12 went to the third group. And 4 out of 12 went to the fourth group. Well, we're taking the weighted average of the same value, b of 1/2. So that would just be b of 1/2. Which is 0. So the information gain is 0, which in turn means when we use type as the decision point, we don't get to reduce entropy at all. But if you consider the Patronus example, in the first group, we have entropy of b of 0, which you know is 0. In the second group, we have entropy of b of 1, which you also know is 0. And then the third group, we have entropy of 2 out of 6. If we were to compute the information gain for Patrons, we have b of 1/2 minus the weighted sum of these, which would be 2 out of 12 times 0 plus 4 out of 12 times 0 plus 6 out of 12 times b of 2 over 6. So we have b of 1/2 minus 1/2 b over 2 to 6, which we know is greater than 0 for sure, because 50% is more uncertain than 33%. So this means that when we use Patronus as a decision point, we get to reduce the entropy, so we have some positive information gain. So we can consider all remaining attributes and select whichever one has the biggest information gain and use that as a split point. And then from the remaining ones, you use the attribute with the biggest information gain and so on and so forth until you end up with nodes that have examples of the same class, which doesn't have to be split further. And there are some heuristics you can use to shrink the tree size. One is decision tree pruning, in which case you replace some of the uninformative attribute nodes with leaf nodes of the descendants. Or with early stopping, you can stop building the tree when none of the remaining attributes really gives you big enough of information gain. So in both of these cases, you might end up with leaf nodes with examples from different classes. In such cases, you can either assign the node default class, yes or no, whichever one is the default one in the previous example. Or if it's a regression problem, you can use the percentage of yes nodes in the leaf nodes. If you have attributes with infinitely many possible values, you can consider different split points and see which one gives the best split of the training data. In this case, it happened to be 6 p.m. For regression problems, instead of associating each leaf node with the specific class, we can associate it with the specific function so that the outcome of searching through this decision tree is not a single class, but one of infinitely many possible values. The second learning algorithm we're going to look at is called k-nearest neighbors, or KNN. So the idea is pretty simple. So similar examples tend to have similar labels or classes. So the idea behind KNN is to classify a new unseen instance based on the k most similar examples in your training set. If we were to revisit the restaurant example, again, the idea is to decide whether Trump would leave a big tip or not. And suppose you have a new restaurant where the food is great, you can have a good chat, it's fast, price is normal, and so on. You'll find the most similar restaurant in our data set. So the first restaurant has 3 things in common. The second restaurant has 4 things in common. The third restaurant has 2 things in common. The fourth restaurant has 2 things in common. So the second restaurant has 4 things in common. And then the first restaurant has 3 in common, and so on. So if we're doing 1NN, the classification will be based on the class of the second restaurant, which is yes. So we'll classify this as yes. And then for the second example, the closest one is restaurant 3, which has label no. So you would classify this as no. If we use k of 3 and n, then we'll look at top 3 and see the majority class. And k and n used to be the primary approach when it comes to recommendation systems like Amazon product recommendations. So suppose we have 3 users, John, Anna, and Bob, 1 row for each user. And then we know that John upvoted Toy Story, Zootopia, and downvoted Shrek, and didn't vote on WALL-E and Inside Out. What would you recommend to John? So in this small data set, John's closest neighbor is Bob, because they have 2 things in common. Because Bob recommended WALL-E and not Inside Out, we could say, oh, maybe John would like WALL-E too. And this approach is called collaborative filtering, and it used to be largely based on k and n. So let's formalize k and n. So our training data is pairs of vectors and classes. So this is our label or class. So for example, our x1 could be a restaurant with great food, no chat, and so on and so forth. And then our y1 could be 1. So let's say 1 is big tip, small, not big tip. So we have a whole bunch of pairs of restaurants represented by the list of attributes that we defined paired with the correct label or class. And then we have to have some notion of similarity that takes 2 vectors and outputs a real value. So one example could be the number of attributes that are common. And we also have to decide how many neighbors we're going to consider. 1 would be the smallest, and it could be very big. And given this setup, here's how you classify a new example. So given a new example x prime, we take the vector representation of it, and we classify that. So this is the label or class. We classify that to whichever y that maximizes the value on the right. And the possible y's in this example are just -1 and +1. And this thing is a shortcut for saying the value is 1 if yi is y and 0 otherwise. And this is the k nearest neighbors of x prime. So we're basically figuring out how many of the k nearest neighbors has label y. So for example, if k is 1, so we actually have nothing to sum over. And suppose the nearest neighbor to x prime has label +1. Then this whole value would be 0 if y is -1 and 1 if y is +1. This would be argmax. Again, if the nearest neighbor of x prime has label +1. So this whole thing is just a fancy way to say majority vote. You consider k nearest neighbors, and the most common label becomes the label of x prime. And there are some design choices you have to make. So the first decision you have to make is to decide which attributes you'll use to represent each example or each data point. So in the restaurant example, we had attributes like food, bar, and so on, but you could have had other attributes also, or you could have taken out some of the attributes. It's important to use informative attributes that are relevant for the task. For the restaurant example, we could have had an attribute for the color of the wallpaper. And I'm guessing it probably won't matter when it comes to deciding how much Trump will tip. The more relevant attributes you have, the better you can expect your classifier to perform, because we're basically throwing away all information other than the attributes we select. So in non-deep learning approaches, you tend to spend a lot of time designing the attributes or features. And there are different types of attributes or features. Some are nominal, so each class has a name, like brown, blue, green. You could also have Boolean features, where the possible values are either true or false. And you could have numeric features. The values could be integers or real values. And you could also have structure features. So for NLP, you could have a parse tree. A sentence consists of a noun, verb phrase, which in turn consists of verb and noun. So that could be your feature for a sentence like AI. And you could also have amino acid sequences as features. And this is a very important thing to remember as you decide on the set of attributes. You may have heard of the phrase curse of dimensionality. And this basically means if you have too many features or too many attributes, your performance degrades. So here you have a graph where x-axis is the number of features and the y-axis is the performance according to some measure. So initially, as you increase the number of features, the performance improves, but after a certain point, it starts decreasing. Given some fixed size data, perhaps this visualization will make it clear. So we have a case with 8 examples, 3 classes. And in the 2D case, where we have 2 attributes or features, the 8 examples more or less fill up the space. If you have a new instance here, it will be labeled as circle. Anything here would be labeled as square. Something here would be labeled as triangle. If you look at the 3D case, the same examples no longer fill up the space. So if you have, it's hard to draw, but if you have a new data point falling right here, we can't really tell whether it should be a triangle or square. You probably need a lot more examples to have a well-performing classifier. For KNN, we discussed how we need a way to quantify the similarities between examples. And there are many ways to do this, but pnorm is one popular approach. Pnorm is a general description of a class of norms where, depending on the p, the exponent here, and the root gets its value. So if p is 1, you have this, and it's called 1 norm. And if p is 2, these are 2's, and it's called 2 norm. And how to use this to quantify the similarity of 2 examples? Well, first of all, this x is an n-dimensional vector. And we set x as a difference between 2 examples that we're considering. Then 1 norm becomes the summation of vi minus wi, which you already know as the Manhattan distance. So let's say v is 0, 0, and then w is 1, 1. So we have v, w. Then we're adding up the difference with respect to x-axis, which is 1, and then difference with respect to y-axis. So our Manhattan distance is 2, 1, 1. 2 norm, we have vi minus wi squared and the square root of the whole thing. Do you recognize this? It's the Euclidean distance. So in the example above, we have 1 squared plus 1 squared, and square root of that was square root of 2. And that's exactly this distance. And then we have something called infinite norm or max norm, in which you just take the max across the different dimensions. Another thing you need to consider is the k value. So how many neighbors are you going to consider? So we talked about how k would be at least 1, and it could get bigger. And what's the effect? As you increase k, KNN becomes less sensitive to noise. On the other hand, if you decrease k, it makes KNN more sensitive to noise. The idea is to pick k that's not too large, but not too small, which isn't always easy. And here's an example. And we have 3 classes, blue, red, and green. And we're looking at the difference between 1NN versus 15NN. And the lines represent class boundaries. So like any new example mapped here would be classified as blue. Anything mapped here would be classified as red, and so on. And we can see that there are small regions of blue within the red zone. And this makes us think that 1NN may be too sensitive to noise. Whereas if you look at 15NN, the boundaries are much simpler. So that's for blue, green, and red. So when it comes to classification, we can just do majority vote. And this means that setting k to an odd number makes things easy. Because you'll always have a majority class. And for regression, you can't just take majority vote, but we can still do things like weighted sum and fitting a local hyperplane.